A word-level tokenizer breaks on unseen words and wastes vocabulary. Byte Pair Encoding repeatedly merges frequent symbol pairs into reusable subword tokens you can build from scratch. After this, you'll understand how to assemble a pipeline that learns reusable subwords and splits unseen words into shorter token sequences. I'm Professor Pi, teaching AI foundations with simple Python. Tokenizers are the bridge between raw text and models. If you feed a language model only whole words, every new spelling forces a new entry in your vocabulary. That bloats memory and fails on rare words. If you use characters only, you can represent anything, but sequences get long and models learn patterns more slowly. Byte Pair Encoding, or BPE, hits a middle ground. Learn common pieces and represent rare words as combinations of those pieces. In practice, this reduces vocabulary size while keeping sequence length reasonable, which speeds training and lowers memory. At a glance, BPE starts from characters and repeatedly joins the most frequent adjacent pair into a new token. Imagine the tiny corpus with words like play, played, player. Characters plus an explicit end marker show you that the suffix ed or appears often. BPE will learn those pairs, so later you can represent played as play plus ed instead of a completely new token. This saves the model from memorizing every inflected form. We will build a small BPE trainer and an encoder you can run on new words. The goal is concrete. You will see the trade-off between whole words and characters, learn how merges are chosen and applied, and then use the learned merges to tokenize unseen forms. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Let's start by comparing word and character tokenization on a tiny corpus so you can see the exact trade-off BPE is trying to solve. This snippet makes the trade-off visible. Word tokenization produces short sequences for the seen forms, while character tokenization avoids unknowns but expands sequence length. It prints word tokens and char tokens so you can see how the same text maps to very different sequence lengths before we introduce any merges. We now need to detect which adjacent symbol pairs repeat so we can compress them into new subwords. This example identifies the single most frequent adjacent symbol pair in the current symbolized corpus. Starting from characters plus a W end marker, the counter named vocab holds each word as a tuple, and pairs counts every neighboring pair inside those tuples. Sorting before taking max keeps the result deterministic, so repeated runs pick the same first merge. The printed output shows the pair chosen to become the first reusable subword. Finding the best pair is good, but you must actually apply that merge to every word form in the tracked vocabulary. This code performs that update across the vocabulary and shows the practical effect. Repeated adjacent matches of best pair are replaced by a single join token using the merge word helper. The counter rebuild keeps word counts associated with their newly merged symbol tuples, so frequencies stay attached. The output reports the new token and confirms the vocabulary entries were updated correctly. One merge shortens sequences a bit, but real tokenizers learn many merges and keep the order for deterministic encoding. This snippet iterates the merge decision to build a small ordered merge table. Each loop recomputes pairs from the current vocab, picks the most frequent pair, appends it to merges, and applies it to the tokenized words. Running more iterations typically shortens sequences but grows the learned token set. Fewer iterations keeps vocab size down but leaves more character splits. The printed merges show the learned, deterministic order the tokenizer will use. With a learned merge list, The final part is using those merges to encode new words that were not in the training corpus. This example shows how to deterministically encode unseen words with the saved merges. Encode word starts from characters, applies each saved merge in order, and strips the visible end marker from final tokens, so outputs read cleanly. That lets words like lowered reuse low and while wider can reuse a learned der suffix pattern. The final comparison shows raw character length versus the number of unique BPE tokens produced in this tiny test, demonstrating shorter reusable pieces instead of a massive word table or a pure character stream. If you map this toy pipeline to a real project, you train merges on a representative text set like your app logs or Wikipedia. Then you export the merges and apply the same deterministic encoder at inference, so token IDs match between training and serving. BPE is a compact subword method that builds tokens by merging common adjacent symbols. Use it when you need a middle ground between whole words and characters, and when you want deterministic, reproducible tokenization. Remember one caveat: more merges shorten sequences, but increase vocabulary size and memory use. For a practical next step, train merges on your real corpus and tune the number of merges until token sequence lengths fall, while vocabulary size stays manageable for your model and hardware. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.